In the final lecture in Unit 2, we're going to look at section 2.3, Energy from Fuels. When fuels burn, they give out energy, and this of course is known as an exothermic reaction. And this picture may remind you of the apparatus we used to measure the amount of energy given off when a fuel burns. The fuel was normally an alcohol, was in the spirit burner, and we burnt 1 gram of the fuel and measured the temperature rise in a known volume of water. The water was in something called a calorimeter, which in our case was just a copper can. And these results were used along with this equation, EH equals Cm delta T, to work out the amount of energy released on the burning of 1 gram of the fuel. Now this equation can be found in the formula page of your data book. So EH is the heat energy produced by the combustion of the fuels. C is the specific heat capacity of water. It's got a value of 4.18 kilojoules per kilogram per degree centigrade, and this value is also given on the same page of the data book. M is the mass of water that you're heating up, and delta T is the change in temperature from what the temperature of the water was at the start till the end after you burnt the fuel. Now the most obvious mistake to make is in the mass of water. It's in kilograms, and 1 litre of water weighs 1 kilogram. So if you're given the mass of water in kilograms or litres, then that's just the figure you use. However, you're more likely to be given the water as either in grams or in cubic centimetres. In fact, cubic centimetres is most likely. In either case, you just divide by 1,000. So if you have 500 grams, divided by 1,000, you have 0.5 kilograms. If you have 500 cubic centimetres of water, divided by 1,000, you've got 0.5 kilograms. So please remember, M refers to the mass of the water, not the mass of the fuel that you burnt. It's the mass of the water, and it should be in kilograms. It's probably best demonstrated by doing an example. So let's look at this one example. So when 1 gram of methanol was combusted, it raised the temperature of 200 cubic centimetres of water from 25 degrees C to a maximum temperature of 40 degrees C. Calculate the energy given out. So the energy given out is the heat energy, and we use the equation Cm delta T. Look up our data booklet. It reminds us that the value of C is 4.18. M is the mass of the water that was heated up, not this mass, not the mass of methanol being burnt. It's the mass of the water being heated up. It's given to you in cubic centimetres, so you have to divide by 1,000. That gives you the mass of water. It would be 0.2 kilograms. And the temperature rise, it went from 25 to 40, so it rose by 15 degrees. And that comes to 12.54, and the units will be in kilojoules. Okay, so it's really very straightforward. Just use this equation. It's given in the data booklet, as is the value of C. Delta T is very easy. Just make sure you get the mass of water that's been heated up correct. Now, if you compare the result you get with known values, you normally find that your experimental value is too low. And that's because of a couple of reasons. Firstly, we tend to get incomplete combustion in the lab. So we don't have enough oxygen to turn all the carbon in the fuel into carbon dioxide. Some of it only gets turned into carbon monoxide or carbon, which shows up as a layer of soot on the bottom of the copper can. And you probably remember how dirty this experiment was, and your fingers were black. The other main reason for getting a lower value than the true value is due to heat loss to the environment. All the heat produced by the burning fuel does not go into the water. Some of it heats up the air surrounding it, some of it is used to heat up the copper can. It doesn't all get into the water. So for those two reasons, the value determined experimentally in a school lab would be far less than the true value. There's more sophisticated equipment you could do it in industry, but in the school lab you've got those two problems. There's not much we can do about the incomplete combustion, but it's probably could do things to reduce the heat loss. Sometimes you can use draft shields, so you can put a draft shield up on either side and that will reduce heat loss to the environment. Or you could put a lid on top, just a wee hole for the thermometer, and again that also will reduce heat loss to the environment, but you'll never get rid of it entirely. Okay, 3 things you should be able to do. You should know what is meant by the term exothermic reaction. You should be able to use the equation EH equals Cm delta T to calculate the heat produced by the combustion of the fuel. And you should be able to give reasons why experimentally determined EH values are less than the true values.